Hello students, this is Anjana from Computer Science Department. In this class, we are going to discuss about the requirements for the message authentication code and its security. Okay, now let's get into our topic. So basically, what are the requirements that we are going to take for the message authentication? Suppose in the previous classes we have discussed how we are going to authenticate a particular message from a sender to a receiver. Suppose if you want to authenticate that message, what are the if you want to authenticate that message code, then what are the requirements that we are going to have? Now let us see. So a message authentication code is also known as a cryptographic checksum, and it is generated by a function C to form message authentication code of K, M. We can represent it with the letter T, so we can say it as a message authentication code. K is a key and M is the message. So so here already they are explaining about this K and M. Here K is a where M is the variable length message, K is a secret key only by the sender and the receiver. So if only by the sender and the receiver, and MACK, M is a fixed length authenticator, so that sometimes we can call it as sometimes called as a tag. We can represent it with the T, so we can say it as a tag. So the tag is appended to the message at the source at a time when the message is assumed to know or known or correct. Then the receiver authenticates that message by recomputing the tag. So how we are going to generate that tag means, whenever we are at the time we are going to send the message to the sender, we are going to append means what? Add. We are going to add some source to that message, such that that message is assumed or known to be correct. Okay, this is known to be correct, this is a correct message, just like that we will think. And at the receiver, if we add that particular type of tag, then at the receiver authenticates that message by recomputing the tag. We have computed that tag at the sender side. The receiver, what he will do, he will recompute the tag. So here the requirements for the message authentication code is, basically we first for what we need a variable M with variable length message, and K is the secret key shared, and next one it is only by the sender and the receiver, and MAC K comma L is the fixed length, so that when the message is assumed to be known or correct, so the receiver authenticates that message by recomputing the tag. Okay. Next one, in case of message authentication code, it considers it as a sometimes it may be an entirely different concept. In general, message authentication code is finally a many to one function. Due to many to one nature of the function, we are using the brute force method. And how would an opponent attempt to discover a key? And if confidentiality is not, suppose if it is not having any type of confidentiality, then then there will be a chance to hack our message. So if it is not employed correctly, the opponent has the access to the plain. If it is a plain text message and without authentication, definitely that message is having the chance to be corrupted. So in case of that message authentication code, what we have to consider is, here all are the different considerations. Those are, in general, a message authentication code function is a many to one function. That means we are applying many as authentication codes, finally it will give the one output. So due to many to one nature, so it is many to one nature. No, for that reason we are using the brute force method, such that we would have an opponent to attempt a the person who is going to retrieve that data, the third party person, we can say him as opponent. Just like that, opponent attempt to discover a key. So whatever the key that is generated for our message, the opponent wants to discover that message. Then if the confidentiality is not employed, the opponent has access to the plain text messages and their associated message authentication code. Suppose K7N is suppose that the key size is greater than the MAC size. If that key size is greater than MAC size, then given a known M1 T1 and M2 T2, we are going to divide it into the message is divided into the blocks, and for that each and every block we are going to apply this message authentication code. Then it will be represented with the tag T1, tag T2. If how many blocks that we have divided, we are having that many tags. So T1 is equal to MAC of K1 and 1, and the cryptanalyst can perform the TI is equal to MAC of KI. For all possible key values Ki, at least one key is guaranteed to produce a match. Ti is equal to T1. Okay. Next one. So from this we have to note that 2 power k tags will be produced, but there are only a 2 power n6 2 power k different tag values, such that a number of keys will produce the correct tag and the opponent has no way of knowing which is the correct key. On average, total 2 power k or 2 power n, that is 2 power k n keys will be produced for a single message. Also we have to produce that many tags. I have already said in the previous slide that if it is a larger message, it is highly difficult task for a person who is going to send the message to produce that key. So to send that much message, if you have divided that message, then it will be easy for him to generate a key. So based upon the blocks that we have divided, uh, based on that only the number of tags will be present for us. So we have to note that total number of 2 power k tags will be produced, but there are only 2 power n6 into 2 power k different tags values. Thus the number of keys will be produced that the correct tag, and the opponent has no way of knowing which is the correct key. So from this we can say that if the opponent also wants to test the data, he doesn't get any chance to know that he doesn't having any chance that he can't able to know which is the correct key. On average, total 2 power k by 2 power n, that is 2 power k minus n case, will be produce a match, such that the opponent must irritate the attack. Okay, he has to iteration means what? He has to multiple times he has to uh, apply the rule for that. Then it will be definitely a difficult task for the opponent also. So if it is a round one, given m1 t1 is equal to mac of k comma m1. So m1 t1 means for the message m, that t1 is a tag, we are going to apply the message authentication code. So for that message, for this message, what are the message that we have given that we are going to send? For that we have generated a key, so we can say it as a tag. Then we are going to compute this tag. So if you have how many times you have divided, for that many times you have to compute that ti. So the number of matches is 2 power k minus n. Okay, then in round 2, given m2 comma t2, such that mac of k comma m2, for the in round 2 also we have applied just like that. We will perform so many iterations like that up to round n based upon the blocks that we have divided. Okay, given m2 t2 is equal to message authentication code of k comma m2, then compute ti is equal to mac of ki comma m2 for the 2 power k minus n keys resulting from the round 1. So number of matches is equal to 2 power k minus 2 into n. So this is how we are going round 1, round 2, round 6, and so on round n. We are going to apply the computational process here like that. Okay. So here now let us see how we are going to provide the security for this message authentication codes. uh, just like an encryption algorithms and hash functions. When if we can group attack on MAC in two categories, a group attack can be done in two categories. One is brute force attacks and cryptanalysis. So now let us see what is a brute force attack. Brute force attack on message authentication code is a more difficult undertaking than the brute force attack on the hash function. Why? Because it requires known message tag pairs. So let us see why this is so. Suppose if the attack have a hash code, we can proceed the following way. See, given message x within the bit, hash code h is equal to h of x. A brute force method of finding a collision is to pick the random bit string and check if h of I is equal to h of x. The attacker can do this repeatedly offline. Then, when an offline attack can be used on a message authentication code algorithm, and it is depends upon the relative size of the then it all depends upon the relative size of the tag. Okay. See, now let us see what is a cryptanalysis. As with encryption algorithms and hash functions, cryptanalytic attacks on message authentication code algorithms seek to exploit some property of the algorithm to perform some attack other than the exhaustive search. So the way to measure the resistance of the message authentication code algorithm is to cryptanalyze the cryptanalyze is to compare its strength to the effort required for brute force attack. So that is an ideal MSC algorithm which require a crypt analytic effort greater than or equal to the brute force effort. So if it is less than brute force effect, then it is easy to compute. But if it is greater than a brute force effect, so it is somewhat difficult to cryptanalyze that algorithm. So as with the encryption algorithms, what you have performed and hash algorithms. Um, here we have generated these types. So as with the encryption algorithms and the hash functions, the cryptanalytics attacks on the MAC algorithm seeks to be exploit some property of an algorithm to perform the this type of attacks, and that is an ideal MAC algorithm which required to cryptanalytic effect or greater than or equal to brute force effect. Now let us see what is HMAC. HMAC is a special construction for calculating the MAC involving a cryptographic hash function in the combination with the secret cryptographic key. So it is a special that is uh, message authentication code involving the cryptography. We can say it as a HMAC. It is specially constructed for calculating the MAC message such that it is a combination with which the secret cryptographic key, so that MAC is used for both simultaneously verifying the both the data integrity and the authentication message. So hash functions such as MD5 or SHA1 may be used in the calculation of an HMAC. This is then the resulting message authentication code algorithm is termed as HMAC or MD5 or HMAC HSHA1. So the strength of HMAC depends upon the underlying hash function. So the size of its hash output and the size of the quality of the key is depending upon these factors. So here the message authentication code is used simultaneously to verify both the data integrity and the authentication of the message. So the hash function such as MD5 or SHA1 may be used in the calculation of an HMAC. So from this we can say that the size of the hash output and the size of the quality key is somewhat bigger than those of these things. Now let's get into the next slide. So if you have observed this algorithm, this is a key and this is a message. We are going to perform the XOR here we are going to perform the XOR operation After generating that one, here we have dividing it into the bits. Okay, so we are applying the hash function on that particular message. So we can write it as s comma m. So again and again we are going to perform the iterations like this. Finally we will get the message for the key, each and every block. This is first one, this is second one, this is third, up to so many. Okay, just like that we are going to design the HMAC algorithm. Here here we have seen that L is the number of blocks in M, B is the number of bits in the block, and N is the length of hash code produced by the embedded hash function. So if you come to this one, then you can clearly know about that. So here the overall operation of HMAC is defining the following terms. Capital H is equal to embedded hash function. These are the examples of the hash functions. Next one, initial value input to the hash function. Next one, message input to HMAC including the padding specified in the embedded hash function. Okay. Next one, the ith block of M, comma 0 less than or equal to I less than or equal to L minus 1, where L is equal to number of blocks in M, B is equal to number of bits in a block, N is equal to length of the hash code produced by the embedded hash function. Next one, K is the secret key. Recommended length is greater. The length should be greater than or equal to N, and if the key is greater than B, then the key is input to the hash function to produce an N bit key. Okay, these are the overall operations when you are defining the following terms. So if you observe this one, K plus is equal to the key paired with zeros. So already we have generated a key. So if you have padded any zeros for that key, K paired with zeros on the left, so that the result is B bits in length. Okay, then let us see what is I pad. It is 36 hexadecimal repeated B by 8 times. O pad is a 55C hexadecimal repeated in 8 times. So the HMAC can be expressed as the message authentication code of K comma M is equal to H of K plus XOR. This is the XOR operation. We already know about the XOR operation, how you have to do the XOR operation, and or H and key XOR operation iPad. So this is the, for this we are going to apply for the message. Then we can describe this algorithm as follows. Okay, we can describe the algorithm as follows. Next one, append zeros to the left and to K, and create the B bit starting K plus. Example, if K is of the length 160 bits and B is equal to 512, then K will be appended with 44 zeros. Okay, then XOR bitwise exclusive OR with iPad to produce the bit is this one. So we have to append M to SR, and next we have to apply H to the scream generated in the step 3. And next we have to apply the XOR operation for the key with which upward to produce the B bit block S. And next we have to append the hash result from step 4 to 5, step 4 to S naught. Then we apply H to the stream generated in step 6 and output the result. Okay, this is how we are going to perform this calculations like this. So if you have observed this one, the overall operation of this one is we will define the following terms, where H is the embedded hash function, this is 4 is the initial value, and M is the message input to HMAC, yi is the ith block of M comma 0, L is the number of blocks in M, and B is the number of bits in a block, and N is the length of the hash code produced by the embedded hash functions, and K is the secret key. Recommended length is greater than N. If key length is greater than B, then key input to the hash function is to produce an N bit key. And next one, K plus is a K padded with zeros on the left, so that the result is B bits in length. Next one, iPad is equal to 00111010, that is 36 in hexadecimal. So we will repeat it with B by 8 times. And this next one, 0100111100, that is 5C in hexadecimal. So we will repeat it with the 5 by 8 times here also. So this HMSC function is expressed as HMSC of K comma L is M is equal to H of K plus XOR OPAD, then H of K plus iPad is the iPad of M1. Next, from this we can describe the algorithm as follows. Uh, Append zeros to the length and to the left end of K to create a bit string K plus. Example, if K of length 160 bits and B is equal to 512, then K will be appended with 44 zeros. So XOR is a bitwise with I paid to produce the for B bit block. So we have to append a message to the SI, apply H to the stream generated in the step 3, or XOR operation K plus with the operand to the operand to produce the for B bit block S. So we are going to append the hash result from step 4 to step 8. So uh, we can apply hash to the stream generated in the step 6, and output will be the result. Okay, by this we have finished this concept.